Okay, so we're looking at finding areas under a curve. And before we do that, we're going to look at rules of summations, because we were looking at forming rectangles, a finite sum of rectangles underneath the curve, and finding the area of each rectangle and adding them before. And so we're going to use that summation notation to say that we're summing multiple things. So there's a sum rule and a difference rule. Basically, if you have more than one term in your function, then we can sum all the first term together plus the sum of all the second terms together from I equals 1 to n, or k equals 1 to n. Same thing with the difference. If we have some constant in front, we can pull that constant outside of the summation, and then we could sum all the terms and then multiply it by the constant. This constant rule is also helpful. Basically, it's saying if you're summing just a constant and there's no k term in this case, because it's k equals 1 to n, then basically you're adding that constant n times, or n times c. So for instance, if we had k equals 1 to 5 of 6, the first term would just be 6, plus the second term, which is going to be 6, plus, because there's no k in here, plus the third term, plus the fourth term, plus the fifth term. So this is the same thing as saying how many terms we're adding, which is 1 through 5, 5 terms, all times 6, or 30. Okay, so certain summations, there are rules so that we don't have to sum each term. And so the following rules hold. So if you're summing k equals 1 to n of k, and then we can just look at how many terms we're summing, which is saying n here, all times n plus 1, all over 2. If we were summing k equals 1 to n of k squared, we can use a formula to do this. This is how far we're going in, all times n plus 1, all times 2n plus 1, and we're going to divide that by 6. And if we were summing k cubed from 1 to n, and then that's the same thing as n squared, all times n plus 1, quantity squared all over 4. So how about I give you those formulas right here, and if you need it on the exam, you have them in front of you. You don't have to memorize these. You just need to know how to use them. So recall we were looking at, and right now we're going to say our function is greater than 0. So we're just going to look right now at our function f of x that is above the x-axis, or on the x-axis. And so we were looking at some interval, right, from a to b. We had some curve. Let's say that this was f of x. And we were looking at making these rectangles underneath the curve. And the more rectangles we made, the better estimate we had. We talked about there's a couple of different ways that we could look at the height of this rectangle. We could look at the left endpoint of our rectangle, or we can look at the right endpoint of the rectangle. It ends up being that the right endpoint is usually the easiest one to do, or is the easiest one to do. So I'm going to concentrate on the right-hand endpoint. So let's say that this. So right, if this was a rectangle in here, I'd go up to the height of this. Over. So if this was my next rectangle, I would go up to the height of my curve. And we figured that if we wanted n rectangles of equal length, then delta x, that was equal to the endpoint of my interval that I'm looking at, B, minus the start point of the interval I'm looking at, A, all divided by N. Okay, so we have all these rectangles in here, and we have these different heights depending on how high our function is at that value. So notice that our width in here, right? This is delta x. And so if I wanted to get my right endpoint, let's call it C sub k. To get to this first one right here, right? This would be my A value, where I'm starting A plus delta x. But let's say I wanted to get to the second endpoint, right here. I'd have to do A plus delta x to get me right here. So I can say, depends on how far I want to go over. The third endpoint, I would have to take A plus delta x plus delta x plus delta x. I don't know what that one is. So to get that right endpoint, I can just say it's A plus K times delta x. And that's always going to get me to the right endpoint for my height. So then the height is f of C sub k. My width is delta x. So if we want to sum all of these areas, we can write it as the summation of the height, f of C sub k, times the width, delta x. And we're starting when k equals 1. That would get us this first right-hand endpoint to k equals my B value, actually. K equals n, right? Because I have n rectangles. So the more rectangles I have, the better estimate. So let's look at this actually as the limit as n goes to infinity. And this is going to give us the area under the curve. I have to put on the stipulation right now that our curve is above the x-axis. So f of x is greater than or equal to 0. We'll talk about it later when part of a graph or all of the graph is below or falls below the x-axis. Actually, let's just quickly talk about what's going to happen there, right? If you have part of your curve below the x-axis, and we're talking about finding the height, and that height, right, is on the curve, notice if it falls below the x-axis, we're going to get a negative value for our height. And so that's where we have to be careful about where is this graph falling above and below the x-axis. If it falls below, then I'm actually subtracting off. This area underneath is going to be a negative number, and I have to be aware of that. But we'll discuss that in cases we do have it below the x-axis once we get it down that way it's above the x-axis, how to find that area. Okay, so this was for the right endpoint. You can also do this if they ask us to find the left endpoint or the midpoint. Sorry, the left endpoint. So it said left endpoint. So C sub k is equal to k plus k minus 1 times delta x. So if I start with k equals 1, notice that would make this piece 0. If k is 0, I mean, if that makes this piece 0, and I multiply 0 times delta x, that means I'm staying at my value of a, and that's going to give me that left endpoint. If I let k be 2, right? That would give me 2 minus 1. That would just get me over 1 delta x. That would give me this endpoint. And then the midpoint endpoint. My C sub k value is going to be a plus, I need halfway from a to the middle. So that's going to be k minus 1/2 delta x. Anyway, we decide to do it. This is going to be the area. It ends up, it really does not matter what endpoint in the long run that we choose, because it's going to have an infinite number of rectangles in here. Basically, that's going to be just lines that fill this in. Okay. So now knowing that, let's put this kind of all together and start trying to find some areas under the curve using this rule. So the example in front of us, we're given the function f of x equals 1 minus x squared, and we want to find the area over the interval between 0 and 1, looking at the limit as x or n goes to infinity of that summation. And it wants us to use the right-hand endpoint. So let's look at, first of all, let's find delta x. So delta x, our endpoint of our interval is 1, minus the start value of our interval, which is 0, all over n rectangles. So this is going to give me 1 over n. Let's find the kth endpoint, right endpoint. So C sub k in our case, right endpoint. For the height of the rectangle. So this is our a value plus k times delta x. So our a value in our case, we're starting at 0 plus k times delta x. Well, we just found out what delta x was, right? Delta x was 1 over n. So our C sub k value is k divided by m. So we want to find the height of each rectangle. So that means we're looking at f of C sub k. or f of k divided by n. So if we go into our function, right, f of x, and wherever we see an x, we plug in k over n. So we have 1 minus, we see an x there, quantity squared. So 1 minus k divided by n quantity squared. So this is equal to 1 minus k squared over n squared. So the area of one rectangle well, it's f of c sub k all times the change in x. And our change in x, delta x, is 1 over n. So to find the area under the curve, we can look at the limit as n approaches infinity of the summation. We're starting when k equals 1, and we're going to k equals n of, I guess I could have gone this a little further, f of c sub k we already found, right? F of c sub k, that's that 1 minus k squared over n squared, all times f of c sub k, all times 1 over n. So technically I can distribute this 1 over n to each term. So let's bring down the limit as n goes to infinity of the summation from k equals 1 well, 1 minus k squared over n squared. Okay, so just stringing the 1 over n, I have 1 over n minus k squared all over n cubed. So I can break this down a little further. Notice this is like summing, or there's a difference of two separate fractions, right? And there was that rule at the beginning that says if we have a summation of a difference, we can look at the, so I can look at the limit as n goes to infinity of this first piece. Actually, it doesn't matter. Okay, of this first piece. So k equals 1 to n of 1 over n minus the summation from k equals 1 to n of k squared over n cubed. Notice that first summation, that 1 over n, doesn't have a k in there. So if that doesn't have the variable that we're using, where we're starting, then think of this as a constant. So recall that that told me up here, if we had a constant, then it would just be this n times whatever that constant is. So in our case over here, this is going to be n times, so I have the limit as n goes to infinity of 1 over n times this n minus the limit as n goes to infinity of the summation of k equals 1 to n of k squared over n cubed. Or think of this as 1 over n cubed times k squared. So this 1 over n cubed, again, is like a coefficient. So we can bring that outside of our summation by rules of summations. So this first piece, n times 1 over n for that limit, well, that's the limit as n goes to infinity of 1 minus the limit as n goes to infinity of 1 over n cubed times the summation k equals 1 to n of k squared. This was one of our special formulas. I have it in front of me. Okay, that's where I wanted to bring it down. Let me just bring it down over here. Okay, so for this k squared, we can rewrite it. Remember, if we took the limit of a constant, that was just the constant. So this limit as n goes to infinity of 1 is just 1, minus the limit as n goes to infinity of 1 over n cubed times, so let's plug it in here. So we have n all times n plus 1 times 2n plus 1 all over 6. So we have 1 minus the limit as n goes to infinity and 1 over n cubed. We could put that in the denominator if we wanted to. Let's do that. Let's put that n cubed in the denominator. We're going to need to distribute this out, so we might as well start. So n times n plus 1, that's n squared plus n, all times 2n plus 1, all over 6n cubed. And then if I distribute this out, I have an 2n cubed plus n squared. Distributing my n times 2n is 2n squared plus n all over 6n cubed. So simplifying, I got 2n cubed plus 3n squared plus n all over 6n cubed. Well, we get infinity over infinity. That is an indeterminate form. I could use L'Hopital's rule, but I see I'd need to take the derivative 3 times before that even would fall out. Or we can use the rule of infinity over infinity. We could multiply both the numerator denominator by 1 over n to the highest power of the denominator, which is cubed. So this would give me 1 minus the limit as n goes to infinity. So distributing, this gives me 2 plus 3 over n plus 1 over n squared all over 6 over just 6. And remember, we have the denominator goes to infinity, the numerator doesn't, that piece goes to 0. So those go to 0. So we're left with just 2, 6. So we have 1 minus 2, 6. Or 1 minus 1/3, which is equal to 2/3. Okay, so that area under the curve is 2/3. Okay, so it gets a little tedious, and we'll learn an easier way to do this, but this is the reasoning behind doing the easier method of why we can do what we're going to be doing. So
Is this basically like the formal definition?
Exactly. So this is a formal definition of how to find the area under the curve if it's above the x-axis. So technically, if it's below the x-axis and we don't, if it asks, let's just find the area under the curve, then we need to be careful. We have to look at where is it falling below the x-axis and look at the absolute value of that. So if we have f of x equals 2x minus 1, and we want to find the area on the interval between 0 and 4, if you looked at the graph of f of x, that's just a line. We know what the slope is. We know the y-intercept is -1. And slope is 2/1. So if I rise 2, I would run over 1. So when I know when x is 4, I can also plug that in. I'm going to get 7. So we have this line like this. So I technically could find the area of this. The problem is that this is, again, falling below the x-axis at this value right here. And so there's this little piece of the graph that's below the x-axis. And so when I'm looking at the height, that's giving me a negative value. And so I technically would have to look at this as breaking this down. I could look at the absolute value from what's below the x-axis. So that would be the limit as n goes to infinity of the summation from k equals 1 to 1/2. Sorry, 0. Let me just do this differently. Let's say that we didn't know it was below the x-axis for a second. And let's just say that we went through and we were looking at this limit. So k equals 1 to n. We need to look at delta x. So that's going to be I'm starting at 4 and I'm not starting at 4. I'm starting at 0 and going to 4. So 4 minus 0 all over n, which is 4/n. C sub k, this is a plus k times delta x. So in our case, this is 0 plus k times 4/n, which is 4k divided by n. So I need to look at f of c sub k, which is going to give me the height. So f of 4k/n. So we're just going to go in there wherever we see an x. We're going to plug in 4k/n. So doing that, we have 2 times, we see an x, 4k/n minus 1. So we have 8k over n minus 1. Okay, so that's our height value times delta x. So right now we have the limit as n goes to infinity of k equals 1 to n of f of c sub k, which we just found, 8k divided by n minus 1, all times delta x. And delta x we found to be 4 over n. So we could distribute. So this gives me the limit as n goes to infinity of the summation from 1 to n of 32k over n squared minus 4 over n. So we can break it down as a summation of each term. And I can pull out the pieces that don't have k in it. So notice I can pull out 1 over n squared for that first term. And that would just leave me with, actually I could pull out 32 over n squared. And that would just give us k. Minus, so that second term, basically we could pull 4 over n out. Summation of 1, if you want to look at it that way, from k equals 1 to n. So if we use the formula of the summation of just k, so let's keep that 32 over n squared. This summation here, using this rule, is just n all times n plus 1 over 2. Minus 4 over n times, here's a constant, I'm summing 1 n times, so this is just times n. Let's cancel. So I can simplify a little bit. Notice the 2 goes into 32 16 times. If I rewrite this, this is n squared plus n all over n squared, just distributing that n, minus 4. We got infinity over infinity. We can break this up as 2 separate limits. So if we divide every term in that first fraction by 1 over n squared, minus the limit as n goes to infinity of 4. Okay, so distributing, we get n squared over n squared, that's just 1, plus 1 over n squared all over n squared. Something's wrong in here. Oh, sorry, all over 1. And look, it looks like something's wrong because I'm getting a negative answer. And I know that most of my area is above that x-axis right there. Something's off.
What
Well,
happened
wait.
to the 16?
Yeah, that's what I was just thinking. I just noticed that. I was thinking the 32, but there's that 16 here. So let's keep that 16 out front. Let's keep that right here. There we go. That's my problem. This should have a 16 in front of it. There we go. I don't get a negative number now. So minus limit as n goes to infinity of 4 is just 4. As n goes to infinity, that 1 over n squared goes to 0. So I have 1 over 1 times 16, which is 16. So I have 16 minus 4, which is 12. This is actually called the net area. If it wanted the area, this is where we had to be careful. And we'll look at more of this when we're dealing with integrals and we can break it up. But this is falling below the x-axis. So we're actually subtracting off this little teeny triangle in here, which I'll blow up. We're subtracting this little piece off of our area. And we can show what that area is by just using geometry, right? If I looked at this, this is crossing the x-axis at 1/2. And so I know that here, if it's crossing at 1/2, sorry, let's do it right here. Then I know what my base is and I know what my height is. And the area of a triangle is 1/2 base times height. So this height in here was 1. This base in here is 1/2. So the area of that piece is 1/2 times my base, which is 1/2 times height, which is 1, is 1/4. Where if I look at the area of the piece above the x-axis, well, this base in here is 1/2 to 4, so that's 3.5. And this height in here, right, from 0, and we said that this was 7. This height in here is 7. So the area of the piece above the x-axis is 1/2 times my base. I'm going to call it 7/2 times my height, which is 1/2. So this would give me 1/2 plus 7/2, or sorry, times 7/2 is 7/4 times 1/2. So this is going to give me 7/8. I should be getting the same exact thing. Oh, I know why. What was my height? My height was 7, not 1/2. So this is 49/4, actually, not, like I said before, 49/4. Here we go. So if I look at 49/4, the area above minus my area below, that should give me my net area of 12. So 49/4 minus 1/4, that is 48/4, which is 12. If I wanted the total area, I would have had to look at the absolute value of the piece below, which we already found, which is 1/4, plus my 49/4, which is 50/4, or 25/2, or 12 1/2. Okay, so there's a difference between total area and net area. And that's why before we were talking about area, that function f of x had to be above the x-axis. Okay, so let's stop there and we'll get into this more tomorrow, and we'll talk about the fundamental theorem of calculus. So you know that has to be really important, right? Because it has calculus in there. It's a fundamental theorem that ties what we're just doing with integration. So finding area under the curve and the antiderivative and tying those two topics together.